Okay, now subtopic simple harmonic motion and uniform circular motion. So we are going to take a look on the relationship between vibrations and also circular motion. Okay, so basically if let's say we considering point P, an object at point P is attached to a turntable and it is rotated, the turntable itself rotated within this direction. This is the direction of the rotational motion or omega angular velocity of the turntable. So on the top of the setup here we have a lamp. So the image of the object P will be cast on the screen below the turntable. So for the image, as the P move to Q, it seems like it is in vibration. Okay, so as it is rotate to this direction, the vibration will be left, right, left, right, left, right. Okay, so means that there must somehow, relationship or correlation between circular motion, right, with the vibration. Let's recall the characteristic of the circular motion, where we have period and frequency. For the period, we know that is equivalent to 2 pi square root m over k. M is the mass of the object, k is the stiffness of the spring. We're talking about vibration within a spring. Then the frequency is 1 over period. Frequency tell us how many complete vibration or circular motion within a unit time. And time or period here is the time required to complete one vibration or circular motion. So when we have the t equivalent to 2 pi square root m over k, to have the frequency we have to 1 over the whole things here. So we have 1 over 2 pi square root k over m, right? Then the angular frequency, the omega involved within the situation given about the turntable just now, is known as omega, equivalent to 2 pi f or 2 pi over t, right? Is equivalent to square root k over m. So how is it? Omega equivalent to 2 pi f, and f is equivalent to 1 over period. Therefore, omega 2 pi over t, or 2 pi over just now 2 pi square root m over k. So from here, see, you can cancel out this, then we have square root k over m. So this is specifically when we talk about mass spring system. Okay. Alright, so now let's proceed with example 13.5. Right, 13.5. So 1.3 times centrifugal of 3 kilogram car is constructed on a frame supported by 4 springs. Each spring has a spring constant of 2 times 10 to the power of 4 Newton per meter. If 2 people riding in the car have a combined mass of 1.6 times 10 to the power of 2 kilogram, find the frequency of vibration of the car when it is driven over a pothole in the road. So kind of becoming, there is a vibration there. Find also the period and the angular frequency. Assume the weight is evenly distributed. Okay, so since we have 4 tires, so for one tire only, for one system of tire with the spring coil, etc., the mass that we're going to consider is 1 over 4. Okay, the whole mass, the total mass. So the mass of the car plus with the mass of the passenger. Okay, 1 over 4 of the total mass will be the effective mass for one tire, for one spring. So it's equivalent to 365 kilogram. Then the frequency is 1 over 2 pi square root k over m. So substitute this, or this is actually 1 over period, right? And then to have period, 1 over f. So this is answer. And to calculate the omega, angular frequency or angular velocity or angular speed without considering the direction, we call it angular speed, is omega 2 pi f or 2 pi over t. Either way, you will get the same answer. Right? Exercise 30.5 will be your homework. Now we proceed with the motion as a function of time. Instead of our point of view in terms of at what position is what the v, now we also may take a look what is the x, v and a at t equivalent to certain required time. Okay, so means that, okay, now we are going to take a look on the x, the position, the v, the velocity and the acceleration as a function of time depending on the time. As we know, it is not constant, it keeps on changing according to the t. So if let's say we have an object moving from initial position to this position, so now the shadow of it, remember the correlation just now, the shadow of it will falls down on point Q. Okay, so this object moving with amount of omega, angular frequency, in this direction, counterclockwise. Okay, so the theta already covered by object whenever it move from initial position, theta 0, theta initial 0 to here, we have theta covered or angular displacement done by this object. In terms of radius, we have A, okay, as the radius from the center of the circular path. And in terms of linear displacement, in terms of from origin, at this position, this object having x and y. X along horizontal and y is along vertical displacement. Right, so from here, okay, we may know the x, the position along horizontal, okay, by using a cos theta. Cos theta will be, right, cos theta x over adjacent side over the hypotenuse, right? Okay, to have x, okay, it will be a cos theta, right? And since we have the information of omega here, okay, we also know that omega is defined as delta theta over delta t, okay, or simply theta over time. So from here, to have theta, we may put it as this, rearrange it, okay. And we also know that omega is 2 pi f, okay, times with a t. So this is actually a theta. Therefore, our equation now may be rewrite as this, or a cos 2 pi f t. So the whole things here is actually theta, which is equivalent to this equation. So from this equation, we may observe that, okay, A is maximum displacement or the radius, maximum displacement, also the radius of the circle, okay. This is constant, 2 pi f also constant because the omega is constant. The things that going to vary the x, okay, is actually time. Whenever the t change, the x also change. So means that from this equation, we are looking at the position as a function of time. So, okay, now this is a graph, sinusoidal wave function of the simple harmonic motion or harmonic oscillator, we call it, right? So for the position, for the x equivalent to a cos omega t, okay, so we have a cos function here, okay, and then to have, this is position versus time, and here we have the velocity versus time. The velocity versus time will be from this position versus time becoming here. V equivalent to negative omega A sine omega t. Alright, on how to have this, actually, what are we doing? We are going to do this kind of idea or concept. V is equivalent to dx over dt. I know you haven't done your calculus. You don't have the mathematics yet, so you just accept what I am telling you. Okay, so the x is a cos omega t over dt. So when you differentiate a cos function, because the one that keep on changing is t. T is part of theta. Theta is a function of cos, so means that we have to do partial differentiation. So means that, okay, again, we are going to differentiate the cos, okay, and then after that we differentiate the omega t, because the one that we want to differentiate is to the respect of t, not only omega, right, not only cos. We want to differentiate something to do with the t, to the respect of time. Therefore now we are going to put the a cos theta becoming negative, okay, negative sine, okay, theta. The theta is omega t. Then after that we differentiate the omega t, okay, to the respect of t. We will left with omega. So from here, okay, we can rearrange the equation. So negative omega a sine omega t, right? So this is for V. Your part, your task, your syllabus is only use this one and use this one. Actually, no need for you to do differentiation. So madam just show here, okay, on how we get this. Okay, the way to do this is not your syllabus, okay, right? And then for A, it's actually dv over dt. So what we're doing, we are going to differentiate the V, negative omega A sine omega t to the respect of t. So differentiation of let me put it here. Differentiation of the sine function will give us a positive cos. Differentiation of cos will give us a negative sine. Why is it so? Then this is about mathematics or calculus. So A here now becoming, again, the one that having t is within the sine function, means that the sine function must be differentiated, then after that followed by differentiation of omega t. So we have the constant there, negative omega a, differentiation of sine becoming positive cos omega t, cos theta, and then after that omega t differentiated to the dt, means that we are left with the omega. So finally we can have negative omega square a cos omega t. So this is on how we manage to get this equation. Right? So a set of, whenever the x is in cos, you just memorize this one. The v is in negative sine, the acceleration in negative cos. Alright? And then in comparison to the equation that we've learned before, when we have velocity as a function of position, okay, we can see here when the x maximum or minimum, the velocity is 0. Because the x is positive a or negative a, right? So when you substitute it here, it will be 0. So please refer to this. Now, from the graph here, when the x is maximum or minimum, where is the x is maximum? Here. X is maximum, x is minimum. Okay, so please refer to the v. What happened to the v? Okay, whenever the x is maximum, the v is 0. whenever the x is minimum, okay, minimum, negative a means minimum amplitude, then the v is 0 again. That is the meaning. This is the correlation. So either we are using velocity as a function of position or velocity as a function of time. Okay, both of them going to give us the same information. So which one to be used? Depending on the questions, what facts and figure given to us, and what question asking for. So depends which one suit us the best at that moment or instant. Okay, then take a look at the second statement here. When x is 0, whenever the x is 0, okay, the velocity is x maximum. X is 0, velocity, maximum value, but in negative direction. X0, maximum, positive direction. X0, v is maximum, negative direction. That is the meaning, right? So goes the same to this. Okay, so when the x is 0, the v become max. It could be positive, it could be negative. Now, third one, when x is a maximum in the positive direction, a is maximum in negative direction. Take a look. S is maximum and positive direction. How about the a, the acceleration? Negative, maximum in terms of value, but then in negative direction. So that is how we read the equation. In terms of acceleration as a function of position, so let's recall this equation. A equivalent to negative k over m times with the x. Okay, so whenever the x is maximum, okay, maximum, the value of this also maximum, the acceleration also maximum, but in negative direction. Okay, whenever the x is negative, maximum, but negative direction, the a will be negative of negative will be positive, right? So the a will be maximum in terms of value, but in positive direction, in opposite to the x. So whether we are going to observe it in terms of this equation, acceleration as a function of position, or we are going to observe according to the acceleration as a function of time, we actually going to get the same information. Okay, so let's have a recap. Okay, in terms of whenever we substitute the omega, right? So initially we have x equivalent to a cos, okay, introduced to you. But then this is actually the omega. Omega t here is actually theta. Don't forget about this. Omega is theta over time. Okay, so theta is equivalent to omega t. So this is omega actually, right? Then to have v is going to be omega in front. Okay, cos become negative sign, omega and omega bring forward, so we have negative a omega sine omega t. Alright, for acceleration, okay, again differentiate the sine, the v, okay, sine function to the respect of time. We will have positive cos, then again differentiate the omega to the front, bring to the front. That is how we get negative a omega squared cos omega t. Alright, so there is a note here, very important, this one. Remember, the uniformly accelerated motion equations cannot be used here. Why is it so? Because our a is not a constant. It's not uniform. It's not average. The v as well is not an average. Okay, it keep on changing with the t. A also, it keep on changing with the change of the t. Therefore, we cannot use all the kinematics equation that you already learn about the 5 basic, or you manage to get 8. Okay, where we have which one? V equivalent to v initial plus at, all this. Okay, delta x equivalent to v initial t plus half a xt square. So all this equation of v squared equivalent to v final square equivalent to v initial squared plus 2a s or delta x or delta y, all this equation cannot be used here. Cannot be used. You have to use this equation, or you have to use another one, which is v equivalent to plus minus square root of k over m a square minus x square, square root everything, or a equivalent to negative k over m x. Either you're going to use this or in terms of sinusoidal wave function like this. Okay, all these three, all the 5, the 8 equation, the common linear and kinematics equation for the uniform acceleration or average acceleration cannot be used here. Okay, because our a is not uniform, it keep on changing. Now we're going to look on the verification of sinusoidal wave nature. So as I showed you before in part 1, okay, the motion of the spring is up and down, but then the sinusoidal wave function, the displacement that sketched on the motion paper will be like this, sinusoidal wave, right? So this experiment shows the sinusoidal nature of the simple harmonic motion, because up and down non-stop is considered as simple harmonic motion because this motion obey Hooke's law. The spring mass system oscillate in simple harmonic motion because the force within the spring obey Hooke's law, that going to always bring the block back to its equilibrium position. Okay, the attachment traces out the sinusoidal motion. Okay, take a look at example 13.6. A. Find the amplitude, frequency and period of motion for an object vibrating at the end of a horizontal spring if the equation for its position as a function of time is given as this. Okay, so what to do? We are going to compare the general equation x equivalent to a cos omega t or 2 pi f t to the given equation. So from here we're going to take a look which one is the a. So the a is 0.25 meters and our 2 pi f t is equivalent to pi over 8 t. From here we are going to deduce the value, the information of our frequency as well as the period. Okay, so for part B, find the maximum magnitude of the velocity and acceleration. So we don't have to consider the direction since the question asking for magnitude only. V max is omega a. How is it? Because take a look, no equation given here. So what is the equation? Since this is cos for x, for the v, okay, we're going to have negative sine omega t. Okay, so from here maximum value of v will be achieved if the function of sine become maximum as well. So maximum for sine theta, okay, for sine theta or sine omega t is actually equivalent to 1. Cos or sine maximum value of that function is 1.0. Only tangent we can have 1 point something. Alright, so if that the case, V maximum will be left with this only, negative omega E. Okay, since the question asking for magnitude, we are going to do the modulus. The negative is dropped. Okay, so this is a answer. And then proceed to figure out the A maximum. So for the A, the equation A equivalent to negative omega squared A cos sine cos again, cos omega t. So again, when we talk about maximum of acceleration, the cost function will be maximum, which is 1. That is how our equation will be simplified as negative omega squared a. Seeing the question asking about magnitude, we're going to use the modulus. We are left with omega squared a. Alright, so this is our answer. Part C. What is the question? What are the position, the velocity and acceleration of the object after 1 second has elapsed? After 1 second, okay, take a look on the solution. So we are going to substitute the value of t here as 1 second, but be careful, take a look on this. The unit of our omega is radian per second times with second. So your theta here is in terms of radian, right? Therefore, you need to change the mode of your calculator into radian mode. Otherwise, you have another option. You are going to convert this value into degree firstly. Then you're going to calculate. This one also you have to convert it into degree. Okay, or it will be easier for you to change the mode of your calculator. The mode of your calculator must be in radian mode. Then you can straight away press or substitute or put in all the values here. Then you get this answer. Okay, please be careful for this part. Now, for the X, for the V, and then finally for the A. Okay, again, you're going to repeat the same thing. You need to make sure that you already change the mode of your calculator in radian mode. Then after that, you can substitute, press in all the values, and you will get the same answer to this, inshallah. Okay, exercise 13.6 will be homework. Now let's take a look on another model of simple harmonic motion, which is simple pendulum. Why is it simple pendulum? We consider there is no friction at all. Once you swing it, it's supposed to be in swing forever. Okay, but we know the real case is eventually it slows down and stops. Okay, but then let's consider the best case scenario. Okay, so if you have a pendulum, must be with a bob, isn't it? So this is a bob of the pendulum, the attached mass. Here is a string, stretch string. Okay, the system is displaced to the right, having theta as the angular displacement. Okay, in terms of arc length, linear displacement, we can put it as symbol as S. Okay, then within this situation, we have the tension experienced by the bob and also the weight, okay, due to the gravitational attraction. So the weight itself now can be resolved into components. We have mg cos theta and mg sin theta. We know that the mg cos theta is the one that going to balance the tension within the string. The one that unbalanced force or becoming the net force that cause the bob to swing is actually this one, mg sin theta. The mg sin theta has a negative direction because it's pointing to the left, or it's in opposite direction to the S just now, because our S is to the right, but then mg sin theta going to bring the bob to the left. So based on this idea, the mg sin theta, okay, is the restoring force within the pendulum. So it's going to obey Hooke's law as well. Okay, even though we're talking about pendulum, not the spring, but the idea of the Hooke's law is obeyed. Okay, that is how we can classify simple pendulum as a kind of simple harmonic motion. Right. So the tangential force, the Ft, is equivalent to negative mg sin theta. Why is it Ft, tangential force? Because it's tangent to the position. This is part of the circular motion, isn't it? So the F here, the unbalanced force here, the mg sin theta here, is the tangential force. Now, okay, the length of the pendulum, don't forget it is capital L here. Okay, in general, the motion of the pendulum is not simple harmonic motion in reality, because eventually it slows down and stops. However, for a small angles, which is not less than 15, which is less than, it should be not bigger than 15 degree. It's supposed to be always less than 15 degree. Okay, we still can consider it is obeying Hooke's law. It is a kind of simple harmonic motion. Since we can have sin theta more or less to theta, so we are going to simplify our equation to Ft equivalent to negative mg theta only. So this force, so since the theta is very small, which is less than 15 degree, sin theta becoming theta only, therefore our Ft just now can be simplified into negative mg theta only. So this pattern similar to Fs equivalent to negative kx, isn't it? So the mg is a constant. Okay, so we can say that this force obeys Hooke's law. Okay, the period for a simple pendulum is 2 pi square root L over G. Okay, if you still remember, we already derived this equation during dimension analysis, right? The power law. Okay, so now we introduce to you that the constant in front is actually 2 pi. Alright, this shows that the period is independent of the amplitude and the mass. It's only depending on the length of the pendulum and also the gravitational acceleration at that location. So simple pendulum compared to a mass spring system. So this is a mass spring system, this is pendulum. So it having maximum kinetic energy, maximum potential energy. At the moment it is displaced to the positive amplitude. Okay, at the moment it reach equilibrium position or theta 0, the V is maximum. Okay, and then it proceed to the left whenever it reach x equivalent to negative a. Now the a is maximum but in opposite direction. Okay, goes the same to this. Okay, and then whenever it reach equilibrium position again, the a will be 0, the fs will be 0. So for this case, the ft will be 0. The v going to be maximum again. So we are going to repeat the same situation to the simple pendulum. The analogy, okay, the same. The idea is the same. Example 13.7, using a small pendulum of length 0.171 meter, a geophysicist count 72 complete swings in a time of 60 seconds. What is the value of G in this location? So we have how many complete swing within 60 seconds. So period is defined of time taken to complete one oscillation. So if you have the total time divided by number of oscillation, so you will have how many seconds? Okay, time needed for one complete oscillation. That is the meaning of period. That is how we know this is a way to calculate the period. Then to have information of the G, we are going to use the relationship of the period, formula of the period, which is 2 pi square root L over G. So rearrange the equation, look for the G. Now substitute all the information given. We have the G is 9.7 meter per second square. Right. So homework for exercise 13.7. That's it. I'll continue to the third part of the lecture for the wave section. Thank you.